Now we're going to look at residuals and R squared, and what does that mean? So first of all, what are residuals? Residuals are the difference between the actual y value for the data point and the predicted y value for the data point. So I created this line right here, and I'm going to try to use it to do a best fit through these points. Now, I do know that the best fit line needs to go through the mean point. So this is the mean of all the points in my set. I'm going to go ahead and click here, and that shows the residuals. So what do you notice about these residuals? Well, here I'm making the residuals bigger because my line is predicting the data will behave like this, when you can see it's not really behaving that way. So what I'm going to want to do is create a line that makes the residuals smaller. Okay, so the smaller those are, the better my fit. And I can show you a residual plot here, and your calculator can do a residual plot. I'll show you how to do that in a little bit. So you can see that these differences are plotted down below my graph, and it just shows how far the predicted is from the actual. So point A, when you have a positive residual, you can see the point's actually higher than predicted. So when it's higher than predicted, that's the individual residual. So if I go like this, you can see that there's actually a pattern here to the residuals, and we actually don't want a pattern. The better our fit is, the less likely we'll see a pattern in the residuals. It'll look more like normal scatter. Okay. So one thing we can do is we can actually look at, I could try to add up all these residuals, but it's not going to be really interesting. So what I'm going to do instead, and in fact they should probably add up kind of, but not quite close to 0 if it's a good fit. This is not a good fit, so they're not going to behave that way. Okay, so when I do this, what I'm doing is I'm showing residuals, the squares created from residuals. So when I square the original residual here, 1.25, if I square it, I get 1.55. And the thing I'm trying to do is make sure those squares are really small. So to do a least squares fit, what I can do is I can move this line, and you can see I have the sum of the area of the squares here. I can move this line until that sum gets really small, and when it stops getting small, then I have, here we go. Oh, now we're getting bigger. So I'm going to kind of slide it back down. 5, 4. That's about as small as it gets. So my best fit is somewhere around here, somewhere in 5, 4. Now, the smaller the squares are, the better the fit. So I adjust the line till the total area of the squares is minimized. And what that ends up with is the same line as my linear regression. So this is the calculated line that we learned how to do last lesson. So a linear regression is often called a least squares fit because we're trying to make the squares as small as possible. Okay, so to recap, the residual is the difference between the true and the predicted values. And if it's positive, that means the true is greater than predicted, the model underestimated. If it's negative, the true is less than predicted, the model overestimated. And when we're doing residuals, always do a residual plot and make sure that you don't see a pattern in the plot. That's usually a good, if there is a pattern, there's a problem with your fit. So let's go ahead and revisit our example from before. And one thing I'm going to do is create a list of residuals using Y1. So the nice thing is your calculator will calculate residuals for you. So first of all, I'm showing the data here from before with cigarettes and coronary heart disease. And the first thing I want to do is create a list of residuals. So I'm going to go ahead and first of all, I need to do the regression like I did before, 4 there. And then this time, the only difference is I'm going to still have the cigarettes, so my X, and I'm going to still have my Y. But now what I'm going to do is actually establish a function after the Y. So I'm going to hit comma here, and then hit vars, and go to the Y vars and say function, right? And then select Y1, and then press enter. So it doesn't look any different from what I did before, but one thing it's done is it's added residual to my statistics list. So I can go up here And I can actually add in, and if I go down there, you're going to see residual there. And hit enter, and it fills it up. Okay, so you can see my residuals right there. And I can actually, there we go. Let me go ahead and put the actual, I'm going to do it again. Stat, name, residual. So I'm doing it twice for you. Hit enter, and it copied in all the residuals. Okay, now I go to stat plot, and I'm going to go ahead and do a scatter plot. And I'm using plot 3 this time. And this time, instead of L1, I'm going to use the residuals as the Y value. And then hit graph. I'm making sure all my other plots are off. And you can kind of ignore that line that's there. I'm doing a zoom stat. This is the residual plot. So you might see the regression line overlaid. So don't worry about that. The fact that we don't see a pattern here is a good thing. So that's how you create a plot of residuals. You basically do your regression, add in a function of y1 or y2, and then it should generate a list of residuals, which you can add to your stat list with the edit, and then you can plot the residuals. So looking at smoking and coronary heart disease, first of all, we had the scatter plot, and this now shows that linear regression that we just did here. And here's the plot of the residuals. So the residual shows no pattern, so the linear model is appropriate. We don't want there to be a pattern there. Okay, so let's take a look at something else, which is called R squared, and explain variance. So first of all, I'm going to go ahead and show the residuals. And the variance in the residuals is the part of the variance that is not explained by the model. So currently this is a pretty bad model. So let me go ahead and move this. And I can really get it good if I show my squares here again, until that number goes as small as it can go. Well, 5, 4. Yeah, 5, 4 was my minimum. So it kind of matches my linear regression right there. Okay, so if the model's bad, then the percentage is low. Okay, so let me go ahead and move this back. So when I have a bad model, you can see the area of the square. I'm going to hide the linear regression. And let me show you the residual plot. So currently, with this model, I have a certain amount of variance in my Y data, which you notice as I'm moving this line, that 2.39 is not changing, because that's just the variance in my data points and the Y values, all right, which is just the standard deviation of Y squared. We haven't talked about variance in a little bit. So if I take my standard deviation Y squared, that stays the same no matter what model I choose. But you notice as my fit gets better and my residuals get smaller, what's going on with the explained variance? Well, the model's explaining more and more the variation until I get it to basically be the optimal model. So I'm getting about, I can explain about 0.96 or 96% of the variance in this picture with this model, with this line. So the highest percentage a model can explain is 100%, which is perfectly linear. So if I got that to 1.0, that would be perfect. How do we calculate it? We basically say we're going to take the variance in the Y minus this variance in residuals here, all right, and then divide by the variance in the Y. Okay, so now look at R squared. So let me do the linear regression, okay? So here's R, and if you square it, you're going to get 0.96. How does that match our explained variance? Well, you should see that it actually matches exactly. And if you want a cool proof of why this works, how can you take that correlation coefficient, square it, and then it tells you what percentage of the change is, or what percentage of variation is explained by the model. And there's a cool proof of why this works, and check in the math box in chapter 8. So R squared is like it sounds. It is R squared, or the square of correlation. The cool thing about it is it gives the fraction of variability of Y accounted for by the least squares linear regression of X. It's a measure of how successful the regression is in linearly relating Y to X. So let's go back to our smoking example and R squared. And I can see that R squared is 0.534. Well, that means it's 53.4%. So the model explains 53.4% of the variability in the coronary heart disease death rate. Okay, so we can attribute roughly 53% to the smoking. All right, doesn't mean we know cause and effect, so be careful about that. So the last thing I want to do, so that's R squared. The main thing is it predicts it tells you how much of the variation is explained by the model. That's the easiest way to say it. Okay, we can also make predictions. So if cigarettes were if the U.S. were to cut its cigarette consumption in half from 3,900 cigarettes per adult per year to 1,950 cigarettes per adult per year, what does the model predict? So this is not R squared, we're just trying to make a prediction here. And basically I'm going to pull up the equation we had last time, and I'm going to stick in 1950 instead of 3,900. And I get a value of 132.98. Now, this is how you write this as a sentence, and you have to be kind of weaselly with your words because you don't want to commit to something you cannot guarantee. And if anything we learn in statistics, we can't guarantee much. All right, so this is how you word it. The model predicts, notice it says predicts. It doesn't say that the CHD rate would drop. It says it predicts that it would drop from 257 to approximately 133 deaths per 100,000 citizens. There is no guarantee of a decrease in CHD death rate since we are dealing with a model, not reality, and there may not be a causal relationship between average cigarette consumption and death rate, no matter how logical that might sound. All right, so now's your turn to continue some practice problems at Chapter 8, 1, 3, 5, 9, 11, 15, 19, 21, and 23, and the answers are in the back of the book. Make sure you use your calculator and get used to doing the calculations with the linear regression.